And here we are again with part 6 of chapter 14. Yes, it's a long chapter. It's got a lot of really, really important ideas. So here we go. We're going to continue on with hypothesis testing. Now, last time we talked about the three basic types of hypothesis testing: the left-tailed, the right-tailed, and the two-tailed test. And of course, what you do is the null hypothesis looks exactly the same. It's the alternative that changes. And we try to collect enough evidence to support the alternative hypothesis. Now, there are two possible outcomes when you do a hypothesis test. If we don't have enough evidence to support the alternative hypothesis, then we do not reject the null hypothesis. If we have enough evidence to support that alternative hypothesis, then we will reject the null hypothesis in favor of the alternative. Now, because the decision to reject or not reject is based on incomplete sample information, there is always the possibility of making an incorrect decision. Now, very quickly, talking about the null hypothesis. The test is designed to assess the strength of the evidence against that null hypothesis. Now, remember, and also that the null hypothesis is a statement of no effect or no difference. And it always has equality in there, some statement of equality. When performing a hypothesis test, we assume that that null hypothesis is true until we have sufficient evidence against it. It's very, very much like our United States judicial system, that an innocent person is innocent until proven guilty. The alternative is what we're trying to test. We're trying to find evidence to support that claim. It is a statement that there is an effect, that there is some sort of difference. And again, we need to find evidence to support it. The alternative hypothesis should express the hope or suspicion we bring to the data. It is, now, this is very important. It is like cheating to look at the data first and then frame your alternative so that the alternative fits what the data shows. Generally speaking, in your mind you have some sort of question and you want to go and prove it. So you don't want to just collect data and willy-nilly state these null and alternatives. You have to have some reason why you're doing the test. So please read the problem first, set your null and alternative hypothesis, and then look at the summary of your data. So we're going to go through this case study, sweetening colas. Diet colas use artificial sweeteners to avoid sugar. These sweeteners generally lose their sweetness over time. Trained testers sip the cola and assign a sweetness score of 1 to 10. The cola is then retested after some time, and the two scores are compared to determine the difference in sweetness after storage. So, very important that the bigger the difference indicates the bigger the loss of sweetness. So here we've got some of our suppositions. We know that for any cola, the sweetness loss scores vary from taster to taster according to a normal distribution with a standard deviation of 1. The mean for all tasters measures the loss of sweetness. Now, the sweetness losses for this new cola, as measured by 10 trained testers, yielded an average sweetness loss of 1.02. Do the data provide sufficient evidence that the new cola lost sweetness in storage? So remember, to have 0, if our mean had been 0, that would have meant no sweetness lost. But in the slide just above, it said as the number increases, the more sweetness is lost. So from here, it looks like our sample's telling us that, yeah, some sweetness has been lost. But is this mean enough for us to say, hey, the new cola lost sweetness in storage? Now, we're going to go through more of the logic of a hypothesis test and how we're actually going to do this hypothesis test, but you'll see that how the answers will coincide. But this is the general, let's look what happens here. Now, our mean should be 0 if there was no sweetness lost. Now, we have a sampling distribution of X bar from 10 taster, and they told us that the mean should have been 0, because that's in the null hypothesis. We would assume 0, and a standard deviation of sigma divided by the square root of n, which gives us a standard deviation of 0.316. So in this distribution of our null hypothesis, where the mean is 0, this is assuming that sweetness isn't lost, our mean being 0 with a standard deviation for our sampling distribution of 10 tasters to have a standard deviation, one standard deviation being 0.31. Look what the data gave us. The data gave us a data point at 1.02. That is more than 3 standard deviations from the mean. That's not very usual, is it? It shouldn't have happened. If the mean was really 0, that particular sample mean should not have occurred, which is a strong indication that sweetness is lost, that the null hypothesis isn't true. So from our sample, we are gathering up enough data, enough information to support the alternative hypothesis, which tells us that there is a loss in sweetness. So now I haven't given you any numbers, how to do a hypothesis test in general, just how to kind of look at the data, see what's going on, and say, yeah, if I took a sample of size 10, and it really was that this new cola shouldn't have lost any sweetness, I should get a mean somewhere close to 0. And look at this, and a standard deviation in that distribution was 0.3, so really I shouldn't go even any more than 0.6 away from 0. And I'm at 1.02, that's a lot. So that gives us a really good feel that, hey, I don't think that the null hypothesis is true. The null hypothesis distribution can't be correct if I got a sample, or is probably not correct, rather, since I got a sample that yielded such a large number in that distribution. So what we're looking right now is at the distribution of the null hypothesis. That is, so let's look at this. The null hypothesis distribution is where the mean is 0 and a standard deviation is 0.316. If I took samples of size 10, I should be well within at least 2 standard deviations from the mean, generally speaking. When you get further than 3, you are talking about some very unusual occurrences. In other words, things that are statistically significant. That should not have happened. That's a good indication that this null hypothesis distribution just might not be true. So we're going to quantify that. That's what hypothesis testing will give us. So if we really started to formally write up this problem, we'd first have to write up our null and alternative hypothesis. So our null hypothesis is that there's no sweetness lost when we do storage of this cola, this new cola. So our mu would equal 0 in our null hypothesis. The alternative would be that we think that it does lose sweetness. And remember, the number gets greater. So we'd say that our alternative hypothesis, H sub A, is mu is greater than 0. So this is a one-sided right-tailed test. So here's another example. Now I'd like you to read this problem and state the null and alternative hypothesis. So let's see how we'd write that up. Now the null hypothesis is that there is no average difference in the scores in the population of assembly workers, while the alternative is that it's different. So this is going to be a two-tailed test. And we're going to determine if any type of difference exists. So once we determine our null and alternative hypothesis, another thing that what you would do is that you're going to have a sample of a certain size. And you're going to take that, a simple random sample from your normal population, and you're going to calculate its mean. What you do with that, once you calculate the mean of whatever your sample is, you're going to see how many standard deviations that mean you just calculated of a certain size, how far that is in the null hypothesis distribution. And that's this thing called a test statistic, this thing called Z0. Now, your book doesn't use the Z0, doesn't have the naught in there, but I like to keep it in to show you that we're seeing how many standard deviations our sample is away in the mean from the mean and the null hypothesis distribution. So that you realize that we are assuming that null hypothesis distribution to be true, and we're taking our sample and saying, hey, if I take a random sample of a certain size, if this null hypothesis distribution is true, how many standard deviations is it away from the mean? And if it's way too far away from the mean, that's a good indication to me that the null hypothesis distribution is probably not correct.